Hello and welcome back to the second part of today. We are gonna start talking about continuous distributions and in particular about the normal distribution, the one and only we're gonna use most of the time, and it's the most famous obviously. So what is it all about? So let's think again about binomial distribution, like the coin flip. And I flip my coin 10 times. Let's make it a non-fair coin just so the distribution is not completely centered, so we see a little bit more of the shape. So let's say a probability is 0.3. Yeah. Then in blue you see my binomial distribution. So what are the chances in 10 coin flips to get like 1 or 2 heads, or 3 most likely, and 4 and so on. And I've put the normal distribution in yellow in this yellow curve, so we already see like a similarity there. And then if I go up with the number n to 20, 50 coin flips, 100, 200, 200 is the maximum, then we see they just look the same. So yeah, what does it look like, the normal distribution? So the idea is it's kind of the continuous version of binomial. The density looks like that. This is the formula. It's got an exponential function minus and the distance from the mean value squared. So this is the probability density. This little the bell-shaped curve. Some of you who grew up in Germany and still remember the old 10 mark note, then that's the Gaussian bell curve as it was printed on there. And then the CDF is this one here. Not very spectacular, but it does everything a CDF needs to do. It starts at 0 and it ends at 1 and only goes up, up, up. Okay, we're not going to use that formula much because the density, continuous variables, doesn't allow you to do very much. We always need the CDF, we need the integral, because we're talking about intervals. The probability of like getting one exact value is 0, so that's not very useful. And as it happened, the CDF doesn't have a closed algebraic form, so that you can't really integrate the formula. So it's called the error function. We just refer to it as like capital Phi of z, and what it means, it's the CEDF starting from minus infinity, integrating up to this point z. We're also going to use the standard normal distribution. So we talked about standardization, so no reason to kind of keep the mean value, the expectation value mu, and the standard deviation at random values. We can always like shift and scale, so everything works. So we're going to use the standard normal distribution, sometimes referred to with this symbol n of, this is the mean value, expectation value 0, and this is our standard deviation of 1. That looks like that. There's the PDF density, and this is the CDF, the cumulative density. Okay, and obviously for large numbers, then all the discrete distributions we talked about last time and this time, they all converge towards it. So binomial we use now in the comparison, but the Poisson is basically just a special case of binomial for large numbers and small probabilities, and hypergeometric was like the same as binomial for large numbers anyway, so they all converge to the normal distribution. We also see that, just to highlight the importance of this distribution, a lot of things in nature kind of, or like natural processes and physics measurements, everything kind of follows the normal distribution. We're going to see later a little bit why that is. It's got to do with the fact that the sum of random variables in various distributions kind of creates a normal distribution. That's kind of a weird effect, but more about that later. So what else can we say about it? Yeah, because it's so widely used, people have created like little tables like this one, and you can sometimes memorize some key facts. So within 1 sigma, that's often like said, so within 1 sigma around mu, you get something like 68% of data points. Yeah, so if people give you say, this is what we measured and sigma is this value, then like within this like error value they give you, 68% of data points fall into, and if they give you 2 sigma, then it's even more. It's more like 95 point something. So then you're like already fairly confident. And there are different ways of describing this. Here like cumulative percentages, which is basically just for the places where the sigma is the value of the CDF. Here the percentiles, we talked about them in the first lecture. So also they describe how this curve goes and where to find things. There's something like Z-scores and T-scores. Different ways of just describing it, like from the military standard 9, more American thing, I think. We won't use all of those, but if you're interested, like look them up. Okay, how can we work with a standard normal distribution if the density is not that easy a function, and we need to integrate, and that integral doesn't even exist analytically in a closed form? Well, we want to use tables. That's how it used to be before computers got available. So we're going to do the same thing. Obviously at home for your homework, or later in industry, you're going to use MATLAB or other programs. But for understanding, that tables are just fine. They give us exactly the accuracy we need. And the thing with the tables is you don't want to write down too many numbers. So we want to exploit the symmetry of our distribution to keep the table small, and it also helps the understanding of what's going on. So the symmetry obviously is this mirror symmetry with the vertical axis. So if I just draw the curve again roughly, then you see the symmetry left and right. Phi of here's minus x and here's x, and they both have the same value. This is the first one here. Then if we look at, so that's the obvious symmetry of mirroring with the vertical axis. If you look at the CDF, the cumulative function, then obviously if I look at this here, this area, that is the same as this one up here, because it's also mirrored. So the cumulative value at x is also like the whole area 1 minus phi of minus x. Yeah. So it doesn't matter whether I look at x and take the area on the left hand side of the point, or if I take the mirrored point and look on the right hand side. We often need the integral from a to b. Then that simply is phi of b minus phi of a. Top point minus bottom point, just like in mathematics. In the special case that we have a symmetric interval, so we go from minus a to a, that simplifies into this. And the reason why I want this minus a here is, if you look at the table, and I'm going to show you how the table is used in a minute, the table has like only negative set values here. It doesn't need to be like the one with positive ones exists as well, but I'm thinking the negative ones are more intuitive, because then we're like here on the left side, and then phi of z is just this like left tail down here. Yeah, it's like easy to imagine, easy to draw. Okay, why is the symmetric area like that? Let's just quickly draw another one of those pictures. And obviously, if this is minus a and this is a, and I want this area here, then I can also say this is 1 minus phi of minus a. So phi of minus a is this. And then I need to take off this one over here, and that one is the same one. The other one is also phi of minus a, yeah, because of the mirror symmetry. So I take 2 times off this phi of minus a, and then I get the result that I want. So once we have that sorted, maybe we need to calculate 1 minus 2 phi of minus, I don't know, 3.24, something like that. Then I look into the table, okay, minus 3.24. There's minus 3.2. And then the last digit, the 4, is here. So I go down this column and I arrive at this value, 0.0006. So 1 minus 2 times 0.0006. Yeah, and I can calculate the result with it. So fairly straightforward with the table. Doesn't even take that long, and the precision is exactly what we need. We don't need any more for our purposes. Cool. Let's go into a few exercises, and I've got quite a few, I think 5 different ones, just because the normal distribution is one of the most important ones. So assuming the height of males in Germany is distributed with a normal distribution, with a mean value of 1.78 meters and 6 centimeters standard deviation, what are the chances of someone being shorter than 160? And I've given you 4 possible ways of calculating this. Which one gives you the right answer without needing the table? And then in the second step, you can look it up in the table that's here on the left and find out what the exact value then is. Have you done it? Okay. So number 2 is right, because let's just have a quick look again. this is our distribution, and we have our mean value is like 1.78, and then we've got 0.06 meter standard deviation either side, and then we're looking at 160. And the key thing here is that, this is 1 sigma, 2 sigma, this is exactly minus 3 sigmas here. Yeah. With 3 sigmas out, so when we look at the standardized normal distribution, we know that we just look at minus 3, which, with sigma equals 1 is minus 3 sigma, is exactly the point here. And then we get the tail here. This is shorter than 160. Yeah, the tail to the left. So phi of minus 3. And if we put that into the table, we can find it here at the top. It's like 0.1% roughly. So 3 sigma is very unlikely. Cool. Let's do another one. What are the chances of being taller than 1 meter 94.2? Exactly this one here. So obviously the other ones are all like trying to trick you, the other answers I've given. Basically you look at the difference, the 1 meter 94.2 minus the 178, that is 2.7 times the 0.06. Yeah, that's what I need to calculate. And then with this 2.7, I can be like, okay, I need so this is 2.7 sigma, this is sigma here. Yeah, this was given. I need taller than that, so I need this end. Instead of looking that up, because I only have the negative values in my table, I go to the left. It's the same as minus 2.7 sigma. Yeah, so minus 2.7 sigma, you can see it in the table, something like 0.35%. Yeah, this is our answer. Excellent. Let's look at another one. The difficulty is going to increase. So what are the chances that there's someone between 1 meter 72 and 1 meter 84? And now without any options, just think about it yourself and calculate from the table. Have you done it? Great. Okay, so we need this one here between those two values, and it's not hard to see that 172 is 1 sigma out, so that's minus 1 sigma, and this one here is plus 1 sigma. So we need in fact just phi of 1 minus phi of minus 1. That's all we need. And then I want to make everything negative because that's what my table is showing, so I can convert it into this one here, and that's 68%. That's exactly what we looked at earlier in the black and white graph when I showed you. Yeah, within 1 standard deviation you get 68% of data points. Awesome. Okay, enough of German males. Let's talk about something more British. Let's talk about baked beans. So a factory wants to fill them with like 160 grams of beans, and obviously every filler machine has a standard deviation. It has a kind of variation in how it gets them in. So there's a sigma of 8 grams. So cans that are considered cans that have more than 170 in are called too heavy. And now those ones that are too heavy are kind of taken to the side. So you basically got a crate just full of too heavy cans, and now you look at those, and what within this kind of too heavy sample, what are the chances of a can containing more than 180 grams? And this is now kind of combining things we learned a couple of lectures ago with the conditional probabilities with a normal distribution. Have you got it? Have you got an idea? Great. So yeah, so what we need is the probability that we're above 180, given the fact that we already know we're above 170. So this conditional probability we can expand to this ratio. So probability that we're above 180 divided by probability that we're above 170. And yeah, then there's not that much to do. I need to see, okay, 180, that's 20 grams above. So 20 divided by 8 is 2.5 sigmas. And 170 is like something like 1.3 sigmas. And then I kind of put that into the formula, and I get like 6%. Perfect. One last one. This is the hardest one. It's almost like taking us a bit to like confidence intervals. So we know that beans are filled with a standard deviation of 8 grams. That's our sigma. Now we've lost the mean value. We don't know what that is, but we've done a trial and we know that 88.5% of cans are less than 200 grams. And given that, you know, everything's distributed normally, what is the mean value? Have a think, pause the video, try to come up with a way of calculating that. Okay, so here's the thing. So I've given you phi of z, 88.5% less than 200 grams. Let's look at the picture. So I've given you this. This is 200 grams, and we know this is 88.5%, leaving us here on the right with 11.5% or 0.115. Okay. So I would get the same thing symmetrically here, and now I can look in my table and I see, okay, 0.115 is something I get at 1.2 sigmas. Yeah, that's the key information. So from 1.2 sigmas out, I get this area. So yeah, instead of like this here would be minus 1.2 sigmas, and the mirrored identical area is up here. So the 200 grams 1.2 sigmas above mu. So then I can put everything into my formula. I know the difference between mu and 200 grams divided by my standard deviation is 1.2, and outcome mu is 190.4 grams. So quite clever how you can connect everything. If you're bored of using the table and looking things up and swinging things around, obviously MATLAB is the program of choice. Normal PDF gives you all you need, or normal CDF. There's also like some additional commands I've put here, so you can fit normal distribution to your data, and yeah, that's quite a powerful tool you've got there. Excel also gives you the distributions, and yeah, that's how you can get started. Alright, thank you very much. In the next video we're going to talk about the hazard function failure rate.